Hi, I'm Mike Dohm, and I'm going to talk to you today about wing size optimization. My objective is to maximize range for cargo transport in order to carry 330,000 pounds of payload. I want to get at least a range of 4,000 miles, which is the span of the Atlantic. I want to optimize wing area, wingspan, and wing sweep, which are basic wing parameters. I also want to vary fuel capacity based off the wing size. I coded my mission in MATLAB, and it does a standard climb, cruise, and descent with reserve fuel. I'm assuming that we're using an off-the-shelf engine and that we're using some similar parameters as the C5, such as operating weight empty, airfoil, and fuel capacity. I'm also assuming that 40% of the fuel is stored in the fuselage and the remainder is in the wing. By holding fuel capacity constant for now and sweeping through a range of wingspans on the x-axis and wing areas on the y-axis, I was able to evaluate the different constraints and find an optimum value. The first constraint is aspect ratio, which should be anywhere between 6 and 12, which are common values for a cargo transport aircraft. This makes for left and right bounds of the graph. The second constraint is range of 4,000 miles, and the third constraint is lift. This forms our design space, and our optimum can be any one of these points. I picked the optimum as the lower left-hand point because that minimizes the wing size and reduces the amount of materials needed to build the wing. This is all for 15 degrees wing sweep. If we end up varying wing sweep by increasing it, we actually find out that we actually reduce the design space. And when we get up to 35 degrees wing sweep, we actually don't have any design space at all. So that shows that 15 degrees wing sweep is actually our optimum point. Now that we've determined that 15 degrees wing sweep is the optimum, we can go forward with that, and now we can try and vary fuel and see what the effect is. What we find is that the 4,000 mile and the lift constraints have changed because they were functions of weight. What was the optimum previously is no longer even in the design space. We actually have two other possible candidates for an optimum value, depending on what you're looking for. If you want to hold 4,000 miles constant, get the minimum range, and get the minimum amount of wing size, then case 2 is what you're looking for. But if you want to maximize range while still keeping wing size relatively small, then case 3 is the optimum value. Some future additions to this wing optimization include performing stability calculations so that we can further optimize the wing sweep, and then also varying some other common wing parameters such as thickness to chord ratio, taper ratio, and airfoils. Thank you.